Hello, students. Today we will learn about electromagnetic induction. And after learning electromagnetic induction, we will move towards applications of electromagnetic induction. So to learn this, first we need to understand about magnetic flux and magnetic flux linkage. For an example, that we do have a surface here, and this surface has area A. Area is actually is a scalar quantity, but it can also be a vector quantity, meaning that it's actually the normal component of this surface area, which is perpendicular to the surface along this direction over here. And now this surface is receiving the lines of magnetic flux density B. And in this picture, that actually at some angle theta from the normal of the surface area A. So in this case, what will happen that the flux passing through this surface will be depending on the angle cos theta. So it means that what is the magnetic flux is mainly the magnetic flux phi that is equal to magnetic flux density B times our cross-sectional area A. When in this case, it is actually when the field lines are perpendicular to this surface, meaning that the angle at 90 is 0. So if the angle is 0, then cosine 0 is 1. So we will have the maximum flux passing through the surface. But if your surface is rotated at an angle relative to the field, or your field is actually at an angle theta relative to the surface, then this flux passing through the surface will be phi is equal to B times A cos of theta. So this concept you could also understand that for an example that we do have a coil, and this coil is like this here, and there is a magnet near to it. For example, here we have a north pole, here we have a south pole. Now, in this case, what is happening? The magnetic field lines are going like this, and now these magnetic flux density, or you can say in simple words, that magnetic field lines that are crossing this cross-sectional area of our coil, which is actually in principle is like a circular cross-sectional area of our coil here. Now, the normal vector is along this direction, which is the area over here. Now, in this case, you can again calculate your flux, which is passing through this coil because of this permanent magnet using this formula here. What in both of these examples, the difference of the magnetic flux or the magnetic flux linkage is only that the flux which is linked to this surface area A, that what we will be calling it, that is the flux linkage, which is telling us that how much flux of a magnetic field is linked to your coil, or you can say any surface of your interest. So this is a simple concept of magnetic flux linkage. Now, with this understanding, we move towards our next main concept of electromagnetic induction. What electromagnetic induction is, for that we can use these two figures. For an example, that we do have a coil, and this coil is, let's say, is winded around an iron core, and this is not necessary. It can also be just simply hollow. And then this coil is connected with an ammeter. This ammeter will measure current passing through this coil. And now in this state, what will happen that this ampere meter will show us zero current. Why? Because this coil is not connected with any source of power, or you can say with any battery. And this coil has a permanent magnet nearby. And this magnet is at rest at its certain position. And now you can see we have a north pole towards the coil. So magnetic field lines will start from the north pole and they will actually terminate at the south pole. So there is a complete cycle. But here you can see that these magnetic force lines that are actually having some linkage over here, over this area of our coil. So we will call it cross-sectional area. So now what we do have, we have a flux linkage of this permanent magnet with our this coil, and our magnet is at rest, it is not moving. So then in this case, we will have a zero current passing through this coil, meaning that there will be no any induction of electric field or electromotive force in this coil, and that what we call it EMF. So now here, if we, for example, change our situation that now our this magnet is moving towards this coil. Now you can see what is happening that, for example, in this previous picture, when our magnet was at a certain position, then you can see about only three lines were crossing, and then now, when we will move toward this coil, more and more magnetic force lines that will be actually crossing this cross-sectional area of the coil. So now what is happening that the number of feed lines in this cross-sectional area is increasing. So in this case, you would say that our flux linkage, the flux which is linked with this coil, is increasing, which we can calculate using this formula. Phi is equal to BA. A is the cross-sectional area times cos of theta. So here, this condition can be considered with the theta is equal to zero. So we are getting actually the maximum flux linkage. Now, when this magnet is moving towards this coil, then your ammeter will show you that there is the flow of current in this coil, meaning that in this actually the wire which we use to make this coil. So now we got non-zero current. This is because of electromagnetic induction. Now, if, for example, you will move this magnet away from this coil, you would see that your magnetic flux linkage will be decreasing when your magnet is moving away from this coil. So again, in this case, you will also get actually the induction of electromotive force, meaning that your current will be non-zero again, but you will note that the direction of the flow of current has been changed. First, if it was going like this, now it is going other way around. So it means that what is happening that when we move magnet towards or away, the flux linkage with this coil that is changing. And this change is actually the main reason of the induction in this coil. So this phenomena is explained by the Faraday's law. What the Faraday's law is, let's try to understand at our next slide, where we will also understand about the Lenz's law. First, the Faraday's law. What Faraday's law is? Faraday's law is a simple law that here, for example, in this first part of this picture, we can see that this flux, which is actually linked with this coil, that coil might have n turns. So now the flux which will be linked with this coil, we actually will have with this formula, phi is equal to magnetic flux density times cross-sectional area cos of theta and times it with the number of turns n, because every turn is actually having the effect of the linkage of the flux. So it means that the total flux for this coil is actually must be calculated using this formula where we have a capital N, and this capital N is the number of turns. Now, this actually, the magnet is moving towards this coil, meaning that it is in. Now, in this case, you can see that the magnetic field direction is here. Then the change in the magnetic field, which is linked to this coil, or in other words, that the magnetic flux linkage is actually changing. And this change is like this, meaning that it is increasing. It is increasing. What? The induction, the induced magnetic field in this, actually, you can say the coil is other way around. This induced magnetic field is actually mainly because of induced current. Because when we have a current, then there will be magnetic field. So now we will have, in this case, this flow of the current. We have a positive terminal here, negative terminal here. If we have a resistance, then voltage will actually develop around this resistor. So which is actually the induced voltage in this coil. Now, if for an example that our this north pole, it is going away. If it is going away, now it is moving away, then now you can see that the change of this magnetic field is actually other way around, meaning that the magnetic flux, which is linked with this coil or flux linkage, is decreasing. And then in this case, what will happen that our actually the induced magnetic field is changing its direction, is changing its direction. So it is other way around, meaning that now the flow of current is actually has changed. If it was like this, or you can say counterclockwise, now it will be clockwise here. This means our induced EMF that will have actually reversed. And previously, we have a positive terminal towards the left and a negative terminal toward the right. And this time, we have a negative terminal toward the left and positive terminal to right. So induced voltage is changing its sign because of this actually the motion of our permanent magnet. Or in other words, you can see that our this induced voltage, and that we can say, for example, epsilon or this kind of E in this coil is actually have the change in polarity. That change in polarity depends on the motion of this permanent magnet. So in the first picture, picture A, our magnetic flux is increasing, and in the B, our linkage flux is decreasing. And with increase and decrease, we actually have flipped the signs of induced voltage. Now, the similar picture you can actually develop even if, for example, you have the south pole towards the coil, and the situation will actually occur if you will actually, for example, moving away from this coil, then you can get the same situation as we actually got when the north pole was actually moving toward the coil. And similarly, in this panel D of this figure, this is actually also the same situation as the north pole is moving to away from the coil, or the south pole is moving towards this coil. Our induced MF polarity is actually the same. So, according to the Faraday's law, that this induced EMF is directly proportional to the rate of change of flux linkage, like this. So, epsilon is equal to d phi over dt. This is the first order derivative of flux linkage. And this one will be equal to actually n d phi divided by the dt. So this n is number of turns in this coil. So this means that our induced EMF will be equal to N. So phi is equal to magnetic flux density times cross-sectional area divided by the dt. It is the first order derivative. So if this our A is constant, then you can say that you have your final formula like Na times dB in terms of magnetic flux density divided by the dt. So first order derivative of our magnetic flux density. So now here, what actually you can do with the number of turns of your coil, cross-sectional area of your coil, and the rate of change of your magnetic flux density, you can calculate that how much induced voltage you would get in your coil. So this is what the Faraday's law is. Now, the question is that what Lenz's law is. The Lenz's law is simply a negative sign in this mathematics. So this negative sign actually indicates that when, for example, in our this figure, panel A, we see that when this north pole was moving towards the coil, the induced magnetic field was like this. So it means that what was happening, that this coil was actually, because this magnetic force lines like this, so it means north pole will be here of induced magnetic field and the south pole will be here. So what is happening, that this north pole is opposing this north pole. So if this north pole is opposing this north pole, that means this coil actually opposing the induced flux linkage, sorry, in rate of increase of magnetic flux linkage. So then if you see in the second picture, picture B, that here the magnetic flux density, which is induced because of the induced current in the coil, it changes its direction. So this means that now we have a south pole over here, south pole over here, and the north pole is here. So this time it is not opposing, but your north pole is moving away. So then north and south, they are reinforcing the flux, meaning in simple words, you can understand it that when you are increasing your flux linkage, your coil will try to space it, and when you are decreasing it, then your coil will try to hold it, meaning try to increase it. So it means that this actually the induced magnetic flux density and the linkage rate of change of linkage flux density, that is actually opposite to each other. And this is actually the reason that you are actually having this flip in the polarity of your induced EMF. And this is what the Lenz's law actually explains. Lenz's law actually explains that the direction of any current resulting from an induced EMF, EMF is electromotive force that we do have here, as epsilon is once again what the Lenz's law is. The direction of any current resulting from an induced EMF is such as to oppose the change in flux linkage that is causing the current. What current? Induced current. And what the Faraday's law is? The Faraday's law is simply the magnitude of the induced EMF is equal to the rate of change of a flux linkage. So this phi is the linked flux with this coil. So this is the Faraday's law and Lenz's law. That is actually the, you could say, the main concept of induced electromotive force in the coil. Now, we actually learned already that when, for example, we apply, we put a conductor in a magnetic flux density, and conductor has the current, so we can actually see in which direction the force that conductor will experience using the left-hand rule. But then in this case, to find the direction of the current of direction of induced current, we can use the right-hand rule. And these rules were explained by Fleming. So we have both left and right hand rules. Remember that the left hand rule is to find the direction of the force on a conductor. For example, that if we do have a permanent magnet, so here we have a north, and here we have a south pole of our magnet. So magnetic flux density direction is from north to south. And what we do, we put a conductor in this magnetic field and the flow of the current is like this. Then now you can use your left hand rule. The first finger of your left hand is along the direction of the magnetic flux. The second finger is along the current. Then your thumb will indicate the direction of the force because of this magnetic flux density on this current carrying wire. What the right hand rule is actually quite much similar. What in the right hand rule, that our first finger is actually the direction of the magnetic field. And here, this actually the left-hand rule, to understand it, you actually need to have a simple diagram again, that for example, we have here a permanent magnet, North Pole, and you do have the South Pole, and magnetic flux is in this way, and you do have some coil inside this you could say the, like for example a rectangular coil in this constant magnetic flux density. And now here, if you move your coil, if you move your coil, the direction of the motion of your coil in constant magnetic flux density, that actually here the first finger of your right hand, thumb is the motion, that in which direction you are moving your coil, and this second finger, it will indicate the direction of induced current in your coil. If your coil is moving up, current is perpendicular to that. If it is moving down, then it changes its direction. If you are not changing the direction of the magnetic field. But now you can also see that if, for example, you change the field and you are not moving the coil, even then, by actually flipping the direction of the magnetic field, your current will also change its direction. So now it means that induced electromotive force, you actually can understand it with this right hand rule, that either you are moving your magnet back and forth, or you are keeping your magnet at a fixed position and you are moving your coil back and forth. So in both cases, you will have the induction, because Faraday's law says that our induced EMF is simply like this, and the negative sign because of the Lenz's law here, that the rate of change of a flux linkage. Now, you actually need to change your flux linkage as a function of time. So whatever the methodology you people adopt to change your flux linkage as a function of time, you will get the induced EMF. There will be no problem in that. So now, to understand our this today's discussion, let's consider two simple cases to understand, or you could say to digest our today's discussion of electromagnetic induction, Faraday's and Lenz's law. So here I consider that what we have a following configuration, that in this configuration, we have a magnetic flux density, which is downwards here. And we do have a conductor. And this conductor, it can actually, you can say, roll over these railings. And now, if this will be actually moving over this railing, which is also metallic, and it is connected with the resistor. So now let's see what will happen in this configuration. So first, try to understand this configuration. Now, here, this conductor, our conducting wire, PQ, it can move on this railing towards up or down here. So when we will move our this conductor PQ towards, for example, this direction, right direction, then you will see that the linkage flux, flux linkage is changing as a function of time. But you can raise a question here that if this our magnetic flux density is uniform, which is in this case, then the flux which is passing through this conductor is in fact not changing. Then what is really changing? We know that the phi is our flux linkage, which is equal to B times A, the cross-sectional area in case of perpendicular situation. So meaning that this is our area, the normal of area is parallel to the magnetic flux. So the cos 0 is equal to 1. Now here, this B is 0. Sorry, B is constant. B is constant. What this area is the area of our this coil that we made with this U-shaped wire, which is also working as a railing, and the conductor PQ. So when this PQ will move, then area, this cross-sectional area, that will change. When this will change, then flux linkage will change. If flux linkage is changing, then its time derivative will be non-zero. So if its time derivative will be non-zero, so you can say in this case that d over dt, that will be non-zero. So it means that we will have a induced EMF in this coil. Now you can actually apply the right-hand rule to find the direction of the current in this coil, and in this actually configuration, when this PQ is moving away, that will be here counterclockwise. Now, In the second example, for an example, we do have here a permanent magnet, north pole towards the left and south pole towards the right. So magnetic flux density lines are from left to right along the as the red lines here. And we have here a rectangular coil inside this magnetic field. Now, if, for example, we rotate this coil clockwise, then let's see what will happen. So in this configuration, our time is 0. At the 0 time, our flux linkage is 0. And this is actually I will explain this in a second. So here, when we will move this coil, then more and more lines will enter into this cross-sectional area of the coil. So when you will move, then more and more lines of the magnetic flux density will be crossing this cross-sectional area. So it means that this flux linkage is increasing. And when this coil's area will be perpendicular, so we will be at max. When it will move next, then this flux getting down to 0 and then again towards negative, because it is actually going, you could say, the other way around, because half cycle and next half cycle. So it is actually the configuration of one complete cycle over here. So let's see that what will happen to the total flux in case of a coil. For example, if you do have n turns in the coil, then we will have this configuration, meaning that amplitude will increase. But in our figure, we have only one coil. So then we will consider this one over here according to the picture. Now, that what is happening here, that the current of our coil, that what will happen, that this will actually have the negative sign, that will have a negative sign. So it is actually other way around, other way around. And the induced EMF is actually will follow this form, this way over here. So here, why this is like this, let's try to understand it in a careful way. This is very important. So that's why we should actually have a look once again. Okay, so if we see that this flux is the curve of the flux is sinusoidal. So we can say it has some amplitude A times sin omega t. So t is time along the x-axis, omega is angular frequency because it is rotating. So you can actually have this one omega over here. And you can also convert your omega into linear frequency with 2 pi f, and this is the frequency, and frequency is equal to 1 over time period. Now, if, for example, we take its first order derivative, then d phi over dt is equal to a constant. Then the derivative of sin is cos omega t, and this omega is constant that we will have here. So now you can see that this flux is actually following sinusoidal graph, and the induced EMF is following what? The cosine graph. So this is the reason that we do have this configuration of induced EMF and the flux. And you can also understand conceptually that, for example, from this configuration, from the time t is equal to 0, when you will rotate it clockwise, then with you can say the very small change, the flux will start to enter more and more and more and more. What once it is perpendicular, then now you would see then the flux will start to decrease. Now, first it is going up, now it is going down. So that is why here at this point, our tangent is zero. So that is why our induced EMF zero, meaning the gradient is zero, the derivative of flux is zero. And similarly, over here, that is zero over here. Good. And you can also see that we do have a negative sign of EMF, and we have a positive sign and a negative sign again. So this is actually because of Lenz's law. Now, here up to this point, if you do have any question or any comment, please leave it in the comments section. We will reply to your all questions and comments as well. Thank you very much for your attentions.